Okay, this is chapter 4, exponential functions. Fortunately, it behaves just as the same in transformations as every other function. It really helps to understand this function, though. It's very much used in science. They want you to refresh your skills with exponents. Exponents power, the power rules, the additional rules. What happens when you take a negative number and have an even exponent? It will become positive. When you have a negative number and it's an odd exponent, it will stay negative. They get you to use the power rule and then realize when this is applied. This is applied within the square brackets, etc. This one's applied outside the square brackets. So you resolve this first and then apply the minus. That's because PEDMAS says you got to do exponents brackets first before you ever multiply it by this minus 1. That's essentially what's going on in front. This is when they want you to realize that a square root is the same as an exponent as a half. And so they want you to get used to that. You have to brush up on your common denominators. Here's the additions of exponents rules. Here's where you have to make the bases the same, etc. All right, and then they go through helping you refresh your skills. And, it looks like that's all there is for this chapter. Okay, they just get you to brush up on the skills. And then 4.1 starts with exploring growth and decay curves. So growth curves are simply when the base is bigger than 1. So if I have y is equal to 1.1, that's bigger than 1. So the standard one is 2 to the power of x. That's a growth curve. And decay curves are when the base, which is that number, is smaller than 1. So 0.9 to the x, which is smaller than 1, is a decay curve. And the standard one, the parent one that they want you to learn, is a half. And this is used a lot in science. For instance, radioactive decay, it halves every term. So you have to figure out what the new amount is based on this equation. And this is very much used in lots of things, which is finance, tracking models of things that grow exponentially like viruses, populations in the wilderness, etc. So both are useful. Both you should be very familiar with. All right, and then they just get you to refresh the idea of what's being measured here and why it sort of slows down as the graph goes on. And it looks like there's not much one in here. It's just showing you what its applications are. 4.2, working with integer exponents. So that's when the exponent is a whole number, but can also be minus. So here they're getting used to powers of 10, which is also very useful to get used to, because in science, when you're dealing at chemistry, the amounts are so huge that you don't write down the number. You just do multiply by 10 to the power of whatever. They do that for acids, bases, all sorts of things, molecules, moles. So get used to your power of 10s and what it means. So they're just trying to explain it to you here, what's the logic behind it, and how to solve it. And this one, for instance, they're getting you to understand what the right side is, what a negative exponent means, and how to resolve it carefully and slowly, not get confused about where your negatives are. And it's very good explanation in the books about how to do things. Where they're not good at is the summary rules, as they kind of put this weird stuff. Notice here, when you have a fraction that's to a negative exponent, you can essentially just flip the fraction and make the exponent positive, which makes sense the more you study it. And they just want you to be more comfortable with them. Well, let's see, check your understanding. Okay. We'll do a few of these, I guess. I'll always do a few, just so that you know, but in this case, I don't think you need to do it. What does a negative exponent mean? It means if it's already in the numerator, which it is, because there's always over an invisible 1 here, you put it to the denominator, 1 over 5, and put the exponent positive now. When I resolve that, 5 times 5 times 5 times 5, I get 1 over 625. So that's what actually 5 to the negative 4 is. It's this. And if you take that to a calculator, you're going to get some weird decimal, 3 or 2 or something. So that's why the fraction is important to understand. This one they're just saying make sure you understand when to apply the negative. So the negative's inside that bracket. So the first rule is, let's just associate the negative. Yeah, let's just keep it there. So it turns out the rule of this is you can just flip the fraction, keep the negative in there, and make the exponent positive. So this is essentially minus 10 to the power of 3. If you want to figure out how to actually do that, the rule of this negative exponent means this whole thing goes to the denominator and becomes a positive exponent. But 1 divided by the fraction is the same as 1 times the reciprocal of that fraction squared. And you can see how we can just flip the fraction. Sorry, cubed. We can just flip the fraction instead and change the thing. That's how we learn why that's true. Now back to this. The reason the negative is important is because when we have a power of 3, it's negative 10 times negative 10 times negative 10. And it becomes positive when these two multiply, but it becomes negative again when this one multiplies. So we end up with negative 1,000. And that's what negative 1/10 to the negative 3 is. And that's much the same, except it's the good lesson here is to know that it also applies to denominators. This is the same as 2 to the power of 4, which is the same as 16, I think. And this they get just you used to flipping the fraction. That's the same as 11 over 3 to the 1, which is just 11 over 3. And this they also get used to the notion that you can just swap their places and keep their fractions positive. So it comes 8 to the 1 to the 7 to the positive 2, which is 8 over 49. If in doubt, yeah, you can do the whole thing the long way. So what happens to the top? It becomes 1 over 7 to the 2. What happens to the bottom? 1 over 8 to the 1. How do you divide two fractions? You take the first fraction and you multiply it by the reciprocal of the second fraction. And you can see that we get exactly what we got before. So they just want you to be comfortable in it. This is interesting here. So they have the same base. So you can add their fractions. What's 8 plus minus 8? 0. So you get minus 10 to the 0. And an important rule is any number to the 0 is equal to 1. So this here is equal to 1. And here they just want you to learn subtractions. What's 8 minus, and careful, it's minus minus 5. Well, that's 13. So it's 2 to the 13 is the final result for this one. And they just want you to get used to the rules of exponents. Okay? Which is a greater power? Explain. Okay? 2 to the negative 5 here is 1 over 2 to the 5, which will become a small number smaller than 1. 1 over 2 to the negative 5 is 2 to the 5, which will become a large number, like 32, I think. So you can see that that's 1 over 32, and this is 32. Which one's bigger? That one. So that one's a bigger fraction. Which is what I think they mean by what is the greatest power. And then they just want you to go through this as well and get your practice in. You should be keeping up with all the chapters, and you should be doing all the practice questions in the back, because the only way your math skills are going to get solid is through practice. So what's the rule here? They're the same base, so you can add their numbers. Minus 3 plus 7 is 2 to the positive 4, which is 16, I think. And again, you can add these. 3 plus minus 3 is 0, so this becomes minus 8 to the 0, which is 1. This becomes 5 to the negative 2 because you subtract their exponents. Minus 8 minus minus 6 becomes minus 8 plus 6, which becomes 3 to the minus 2, which is 1 over 3 squared, which is 1 over 9. So just get used to what a negative exponent is. They're the things that throw students the most. Here is an exponent, a power rule, so you can multiply their exponents. So it's 7 to the negative 2, which is 1 over 7 to the 2, which is 1 over 49. And just do them over and over and over again. This is the same rule. It's just we have a power rule here first. So do the exponents first. And then you have an addition rule. So you end up with 3 to the 3. And when we do the power rule, it's 3 to the minus 2. Now I can add them. What's 3 plus minus 2? It's 3 minus 2. 3 to the 1, which is just 3. So you can see that very complicated thing just became 3. Here I would resolve the power rules first before you do anything. It makes life a lot easier. Again, resolve. Oh, notice the brackets keep this power out. So resolve internally first. And then put it to a -2. And you just got to they're just making sure you practice good math. So here, do the power rule here. 5 to the minus 6. Minus 6 minus minus 6 is minus 6 plus 6. So it becomes 5 to the 0, which is 1. So that whole thing becomes 1. This becomes 9 to the minus 6. So it just becomes 9 to the 7 times 9 to the minus 6, which becomes 9 to the 1. Over and over and over again. And I don't think you need me to do that. Now, these last ones are the trickier ones. So 7. So if you look at there's nothing you can do with it. Now, it's possible to put them to the same base, but there's no real purpose because they're being subtracted. I mean, you could find out how many there are, but the subtraction doesn't really have a rule. So you would really just come up with what they actually mean, which is that, which is that, which is this. What did I do here? I put the 4 as a fraction of 16, which is this. So that ultimately is the answer. Fairly convoluted. I mean, really, you're adding 1/6. You're subtracting a quarter from 1/16, and a quarter is bigger, so it makes sense when you see it written like this. I don't think there's no way to keep just the powers the same because there's no purpose to keeping this to a power of 2 and this to a power of 2 because you still can't add them. They're not the same base, so you still have to change their denominator. What about this one? Go to this one here. So I guess just resolve each first. -3 to the -1 is 1 over 3 plus 1 minus 1 over 6. So they all should be on the same fraction. 6 is the common fraction, so turn this into something over 6. The 1 over 6 is 6 over 6 plus 1 over 6. And if I add up all their tops, I get 9 over 6, which is 1, and 3/6, which is 1.5. This is correct, this is correct, this is correct. Answer in a rational form, so that would mean in the fractionary form. Okay, and it's the same trick over and over again. What's the rule for an fraction with a negative exponent? Just flip them upside down. You don't change the negative of the exponent, of the thing in front. You change the negative of this exponent. So it becomes plus 1, which is just 1. And this just becomes 5 over 2. Now I can add them. What's -3 plus 5 all over 2? It's 2 over 2, which is 1. So a tricky way of saying 1. Five to the 3 is the same as 1 over 5 to the 3 plus 1 over 10 to the 3 minus, and what's minus 8 times 1,000 to the 1, which is that. 5 to the 3 is the same as 625. I don't know if there might be a better way of finding a fraction. This is 1 over 1,000 minus 8 over 1,000, which is minus 7 over 1,000. So we can get it like that, just like that. Now it becomes very complicated to find a common denominator here. You can cross multiply. for sure. If you find yourself really stuck, you just multiply that up there minus 7 times that. Got it wrong. 7 times 625. 4,375. All of it over the two of these multiplied. But you can see what a colossal mess that becomes. And I end up with minus 3,375 over 625,000. Now, clearly they have a 5 in common, and I can keep chipping away like that. I probably suspect there's an easier way of finding it. However, this is a totally legitimate answer, and I could stop here. Not sure if that's what they're going for, but in any case, that's the one that screws it up. And this one's the same thing. 3 to the negative 2 is the same as 1 over 3 squared, which is 1 over 9, minus 1 over 6 squared, which is minus 1 over 36, and then plus 3 over 2 times negative 9 to the negative 1 is 1 over negative 9 to the positive 1, which is that. When I multiply this, I get 3 over negative 3, negative 8, positive 3 over negative 18, which just becomes negative 3 over 18. Negative 3 over 18. I'm just going to keep it like that instead of simplifying it because it's clear I got to go up. So this I have to multiply by 4. This is fine. And this by 2. And I get 4 minus 1 minus 6, 4 minus 7 minus 3 over 36, which is the same as minus 1 over 12. So that's, they just want you to get very adept at working in these numbers. And the only reason that one's kind of important is because you should learn, I thought it was going to teach you, force you to get into new bases, but it didn't. It just wanted you to practice in the rational form. And you can see they get more and more complicated. So what's the secret here? Right? It's just going to be simplifying. So number 8. So if I look at this first one, it's just 25 over minus 10 to the 4, which is going to become positive because it's to the power of 4. So it's going to be 25 over 1, 2, 3, 4 zeros. Now they're both divisible by 25, and I get 1 over 400. And that's all I want you to do. 16 over negative 1 is 1 over 16 times 2 to the power of 5, which I believe is also 16. Let's see. 8 is 3, 2 is 4. Now 32 is 16. 32 over 16 is 2. Now it would have been possible to express 16 as 2 and just keep it as 2 to the 5 up here. And 16 down here could be expressed as 2 to the 4. And you can see, using the rule of subtraction of the exponents, you get 2 to the 1, which is just 2. And you can see they just want you to get more adept with these minuses because they really throw students. All the minus exponent means is send it, if it's in the denominator, send it to the numerator. If it's in the numerator, put it to the denominator. If it's in the numerator, put it to the denominator. So that's all that happens here. Notice the minus didn't change. It's with the number. The only minus that changes in the exponent. So minus 4 over 12 is the same as minus 1 over 3. And that's the answer. And that's what they want you to get comfortable with. Now you have two choices here. You can convert the, oh actually you can't convert, well yeah you could. You could convert the 9 to -2, but let's just make things simpler first. So this down here, let's do the power rule for it first. So we're just going to keep the top the same. The power rule down below says 3 to the -2. Now, since they're both negative, let's rewrite them with positives. That's 3 to the 2 goes to the top, and -9 to the 2 goes to the bottom. Now, -9 to the 2 will become positive. Up here it will become 9. Down below it will become 81. And this simplifies to 1/9. The 81 became positive because the -9 right here had an even exponent that made it positive. And then when you're doing stuff like this, just always remember here that the 8 to the -1 is really a fraction. They just never write it. They just never write the 1 beneath it. So that simplifies to 1/8. These both flip. You can either convert this to 8 or convert that to a power of 2, but let's just leave it like it is. 4 up top when it multiplies, and 8 times 8 is 64. They're both divisible by 4, and you get 1/18. 1/18? 16, sorry. 1/16. This last one's the same thing since they're all multiplying. Notice, don't get tricked by this one. This stays there. It's got a +3. This one goes down, and this one goes up. Now you can convert all those to powers of 5 if you want. So -5 to the power 3 times -5 to the power of +2, because it came up, keeps its minus though, all over -25 to the power of 1. So -25 to the power of 1 is just -25. We'll resolve this before we resolve the negatives, okay? Because you have some exponents here that might change it. Now, I think technically this works out fine because the power, if I add them together, they have the same base, will still be a negative, so it won't affect it. So you get -5 to the 5 over, and we might as well keep this -5 here, and you would keep the minus out. It gets tricky. Let's see. Yeah, well, since we have a minus divided by a minus, I know it's going to be positive, so we can just get rid of their minuses right now. We can convert this 25 to 5/2, and 5 to the 5 divided by 5 to the 2 is 5 to the 3, which is 125. So there you go. That's what happens here. Now you could have resolved these exponents early. 3 minus -2 is -5 to the 5, and you can see how that we got the same result over -25 to the 1. It's the same result, and the minuses cancel. They just want you more and more comfortable with negative exponents, with reason. Wow, they keep doing it over and over again, eh? Until they get into more abstract things down below. And it's interesting down here. It's smarter to resolve these first, as far as you can, and then plug in the numbers. Okay, let's look at this. I'm just going to do a couple. Let's do like that one to see what their point is. The point is, after you resolve the fractions, you need to make sure they can be added together. So the first fraction becomes this. The second fraction becomes this. This has to be resolved first. It became positive because it got squared, and the answer is 9. If in doubt, if you throw that into your calculator, you'll get the same answer. So that would be flip. They'll have the same denominator then, but this one's negative and stays negative. So it'll be -3/2 plus 5/2, which becomes 2/2, which becomes 1. This is just being more and more comfortable. I don't know if I want to do all these. Yeah, it's the same thing over and over again. So they just want you to also to get used to, in this one, what happens to the negatives. So when the first thing you resolve is you still go in BEDMAS. So we have to resolve the exponent first. So we do 1 over negative 4 to the 3. That's what this is. 1 over negative 4 to the power 3. Now, because that's an odd exponent, it's going to keep its negative. So you're going to get 1 over 4 times 4 is 16 times 4, 128, I believe, is 4 to the 3. And if in doubt, take your calculator, and you can either do 4 times 4 times 4. Now, so I got that wrong. 4 to the 3 is 64. Now remember, though, it keeps its negative, so it becomes negative 1 over 64. And that's what they want. They want you to understand when the negative is applied, when it's not. So notice that this is going to become a square, so that negative is not going to matter as much. We resolve the exponent first, so that's 1 over negative 4 squared. And when you square a negative number, it becomes positive. So that solves a lot of your problems. So just keep this negative around. We're going to resolve the exponent first. So you do negative, you can just rewrite it the same way. It's going to be that. Now this negative outside the bracket says that this bracket gets exponented as a positive 5, and the minus 1, the minus is essentially a minus 1 multiplying the whole thing. That's what they mean by this minus. It's going to hang out until you're finished resolving this. Well, 5 to the 3 is the same as 125. And now the minus gets applied, and so the whole thing is minus 1 over 125. I always put, it's stupid to have negatives down in the denominator. It's just there, or even better, you can just put it way out away from the fraction like that. So they're getting used to their textbook notation. Be clear with your teacher. Sometimes teachers have different notation. So this is just saying we've got to resolve the exponents before we ever get to that. So that becomes 1 over negative 5 to the 3. Oh, didn't we just do that one? Yeah, we just did that one. Okay. And they're showing, so you might think, oh, well, there's a square this time, so this negative 5 is going to disappear. No, the negative's outside the bracket. This is the same as 1 over minus 5 to the 2, which is 1 over minus 25. You might say, well, when do I get rid of the minus and when don't I? Well, if this bracket had been on the outside like that, that means this minus 1 is included, this minus is included in the squaring process. When it's outside like that, it's saying, no, it's not included in the squaring process. It's the only way for them to tell you the different situations, which is why they give very similar examples over and over again. So for instance, this minus is not included in the squaring process. This minus is included in the cubing process, but minuses that get cubed are the same. So it's going to be 1 over minus 6 cubed, which is going to be the same as whatever, it's going to be whatever 6 cubed is. 6 to the power of 3. Yeah, 216. And it's the negative sticks around, so it becomes negative 1 over 216. And this one here becomes 1 over negative outside the squaring process, squared, which becomes 1, negative 36, which becomes negative 1 over 36. Both the negatives stuck around, but for different reasons. Least number to highest number. So lowest number to the lowest number. So this is 1 over 2 to the 1 over 2 to the 3, which is 1 over 8. And this is 1 over 9. 1 over 9 is smaller than 1 over 8. And this is 1 over 10. which is smaller than 1 over 9. And this is 1 over 25. And this is 1 over 4. So it's the biggest one so far. This one's interesting. It's 1 over 0.1. And when I take 1 and divide it by that small number like that, I get 10, because 0.1 can fit into 1 10 times. So obviously, 1 over 25 is smallest, 1 over 10 is next, 1 over 9 and 1 over 8 is next, 1 over 4 is next, and then the number 10 is the biggest one. Interesting. I think they're trying to show you that even though this looks like the smallest number, it's not. Oh yeah, so let's see. Yeah, 11. So the smartest thing to do for these is evaluate. Okay. So when I resolve this, it's really 1 over x to the n plus y to the n, all to the 2n. I don't think you can do... There's nothing you can do about this because it would be expanded in that you wouldn't know how many times it's getting expanded. So at this point you would bring in your numbers. X is -2, n is -1, -1. So you can see it kind of messes it all up. Huh. That one's a bad resolution, but maybe if I put in -1 first. So -1 makes that +2. And a 3 here, so I essentially get -2 to the -1 plus 3 to the -1 all to the 2, power of 2. So this is inside the brackets. It has to happen before the exponents. So I essentially get 1 over 2, 1 over -2, so -1 over 2, plus 1 over 3, which is the same as 1/3 minus a half. Cross multiply, I get 2 6s minus 3 6s, which is -1 6 total. So this whole bracket becomes -1 6. And it's squared, so it's times itself. So that minus is going to disappear, and it's going to become 1 over 36. Because when you square it, the 1 gets squared and the 6 gets squared. This one is a good example of resolving it first. Makes it easier. Using the power rule, this is the same, by the way, as x to the n over y to the n to the n. You're allowed to break this up because they're not being added, which becomes x to the n squared divided by y to the n squared. And you'd be tempted to cancel these out, but they're not the same base. And that's the point. You can only do it when it's the same base. So now we can bring in the -2, the +3, and the -1 squared, which just becomes 1. So they just disappear. And you're left with -2 over 3. And again, this one becomes x to the 2n times y to the -2n times x to the -n. So we can add these two because they have the same base. 2n plus minus n becomes x to the n times y to the -2n. You cannot add them now because they are not the same base. You can just say, now I know that x is -2 to the -1, and y is 3 to the -2 times -1, which is y. 3 to the 2, which becomes 9, over -2, which becomes -9 over 2. Might have made a mistake there, but that's the idea anyway. And here you can expand it. Just remember that the x here is also going to get the 2n because it has a 1 there, and the y is also going to get the 2n. So you're going to get x to the 2n over y to the 2n squared, power rule says I multiply their exponents. And these down here get it as well. But let's start with breaking them up. And then they get to the 2n, so that becomes to the 4n squared. And y to the 4n squared. Now, you can still subtract them. It won't resolve much, but you can rewrite it as x to the 2n minus 4n squared times y to the 2n squared minus 4n squared, which is minus 2n squared. Okay, which probably just means I should have left the y down below and left it as divided by y to the 2n squared. Now, interestingly, I can still do a little thing. I can pull 2n out of both of those, and I'm left with 1 minus 4n, 1 minus 2n. Or I can just resolve it like this. So when I put minus 1 into here, I get minus 2, minus 4, so I get minus 6. When I put minus 1 in the exponent down below, I get minus 1 squared, 1 times 2. I get y to the 2. And now I just have to bring back my numbers. So x is minus 2 to the minus 6, and y is 3 to the 2. And that becomes 1 over 9 times negative 2 to the power of positive 6, which will become positive. And I'm a little weak on my 2's to the power of 6's. 64. Oh, 64 times 9. And I'm not entirely sure, 576, but I believe it comes to 1 over 576, which would be 9 times the 64 that this becomes. And this becomes positive because that has a positive exponent. Very complicated. It's much easier to solve it this way, although technically in these cases it might be easier just to do the exponents. Okay, so the error here is that minus came out of nowhere. There shouldn't be a minus there. It just becomes 1 over 3 to the 1, so there's no minus. And the error here is he didn't subtract his exponents properly. It is indeed 3 to the minus 1, and therefore the rest of his solution's incorrect. This here, you can change 4 to a base of 2, so it becomes 2 to the 2 to the minus 2, so it becomes 2 to the negative 4. And when you divide by 2 to the 2, you can then subtract 2 to the 2. So it's 2 to the 3 minus 2 to the 2, so it becomes 2 to the 1 times 2 to the negative 4, which becomes 2 to the negative 4 still, which becomes 1 over 2 to the 4, which becomes 1 over 16. So you can just add them over and over. In this case, you cannot do much with it. You could distribute the 4 through. Let's look at sum of 13s. So as I said, because on this one, you could convert the 4 to a 2 to the 2, and then make it to the negative 2, which becomes 2 to the negative 4. And then you can add it to this 3. So because of the same base, you get 2 to the negative 1. And then it's being divided by 2 to the 2, so you can subtract it. Oh, I got one of the subtractions wrong. Yeah. Which becomes 2 to the negative 3, because minus 1 minus 2 is minus 3, which becomes 1 over 8, not 16. So I just got one of those errors wrong. Probably when I was doing that, like 2 to the 1 became, 2 to the 3, not to the 4. So I just added incorrectly. Okay. Now, what rule they're trying to get you to follow here? Well, that's the same as 2 to the negative 1 times 3 to the negative 1, because the exponent applies to both when it's a multiplier, which becomes 1 over 2 times 1 over 3, which is 1 over 6. If you don't believe it, just multiply them first. You get 6 to the negative 1, and then that becomes indeed 1 over 6. Either way works. Now this here, they want you to apply the negative exponent to both these exponents first, or you could resolve it. I mean, this and this simply becomes 2 over 3. And then the negative 2 applies to both of them, so now you flip them again. You get squared, which becomes 9 over 4. So, nice thing about negative exponents to brackets is the brackets can just flip. But the same thing happens here because they're both to the negative 1, so they both switch spots. Just happens to happen twice. Here, you cannot add the middle. You could solve the middle and add them, or you could distribute. When I multiply these, I'm allowed to add their exponents, so I get to 4 to the 1. When I distribute this, I'm allowed to add their exponents, which still becomes plus 4 to the negative 1. When I add these, I can't really do anything. I have to convert it to their proper fractions, and that's the mistake people would make. So it's 4 1/4, which becomes 4 1/4, or 17/4. I got that by multiplying that together and then adding it to 1. 17/4. You can see 4 goes into 17 4 times and leaves a quarter. So just be careful about when you're adding. You're not allowed to follow exponent rules for adding. And I think that's what they're trying to get you. However, multiplying, fair game as long as they're the same base. Now, notice they're not the same base here. However, this minus switches with this one, and this minus switches with that one, and they're still not the same base. However, these two are, and these two are, which means I'm allowed to subtract their exponents because they're all being multiplied. If they weren't all being multiplied, it couldn't. So 2 to the 5th minus 2 to the 4 becomes 2 to the 1 up top. And 3 to the negative 1 minus 3 to the negative 3. And since I'm keeping it all up top, becomes times 3 to the negative 3. And you have to work with just the top. And then this becomes 2 over 3 to the 3, which becomes 2 over 27, which I think is the right answer. Now notice the 5 to the 0 here is just 1 in the middle, so you could just resolve it first. You're not allowed to do anything. I mean, you could do this first, technically, so long as you kept the bracket there, which becomes 1 plus 25, which is 1 over 26. Even if you resolve the bracket first, you get 26 to the negative 1, which is that. And that we already did. And this is the same technique over and over again. You can only subtract the ones with the same base. But notice here, they want you to notice that the 4 technically could be converted to a 2 to the 2, which would be 2 to the negative 4. So you could replace that 4 to the negative 2 with 2 to the negative 4. And then I can use the same rule. 2 to the negative 4 minus 3, careful, becomes 2 to the negative 1. And then 3 to the times 3 to the negative 1 minus 2 becomes 3 to the 1. And that becomes 1 over 2 times 3, it becomes 3 over 2. Now, the tricky part about this, when I have 3 to the negative 1 and 3 to the negative 2, it's easy to make the mistake and think that's 3 to the negative 3. Now, that would be true if I was multiplying by 3 to the negative 2, and I could add these exponents, plus and minus. But because you subtract in division, minus 1 minus, and whatever the exponent is, minus 2. This minus creates a positive, so I get a minus plus 2. Minus 1 plus 2 is positive 1. That's why I got a positive 1 over here. So be careful. The subtraction is the operation, and then you're subtracting the actual exponents. Find the value of each expression when they give you these values. I mean, no. I'll do 15 for you because it just helps to understand what they're talking about. You should always do as many of these questions as you can. Most tests are based on this. Explain the difference between evaluating that and the second one. Well, this minus 10 gets cubed. So you're essentially, and it's going to keep the minus because a cube keeps the minus. So it's essentially going to become negative 1,000. This 10 to the negative 3 is not anywhere near 10,000. It's 1 over 10 to the negative 3, which is equal to 1 over 1,000. And if in decimal form, I would represent that. That's 0.001. You can see how different that number is from that number. And they're actually, they're 6 tens away from each other because this went in that direction and this went in that direction. So they're very different numbers. That one's negative 1,000 and that one's 0.0001. This is not negative. It's just 1 over 1,000. The negative just means send the exponent to the denominator. Same rule here, except this negative is inside the bracket. So it is going to get cube root just like the 10 is. So that means it's going to become a positive 10,000. And this is interesting, and this is the textbook's way of saying that the minus is not part of it. They should actually be doing it like this. So they're saying evaluate the 10 to the 4 first, 10,000, and then multiply it by minus 1. That's what that minus was. Notice how annoyingly, so you get negative 10,000. Notice how annoying the notation is. They should be much clearer. It wouldn't be that hard to say, okay, I'm talking about negative 10 to the 4, which means resolve this first and then multiply it by minus 1. That's all a minus in front of like anything is. It's really a minus 1 multiplier. Determine what x has to be for this to be true. Minus 1. X has to be minus 1 for this to be true. This one, just understand what 0.01 is. 0.001 is the same as 1 over 100, which means this has to be negative 2 to make it 1 over 10 squared, which is 1 over 100. Well, any number to the power of 0 becomes 1. I repeat, any number to the power of 0 becomes 1. So x must be equal to 0 here. This, again, it helps to understand what 0.25 is. 0.25 is the same as 1 over 4, which is the same as 1 over 2 squared, which is the same as 2 to the negative 2, which means this must be negative 2. Same with this. 25 to the n is equal to 1 over 625, which is the same as 1 over 5 to the 4, I think. 1, 2, 3. Yep. And 25 is the same as 5 squared to the power of n. 5 squared, which is also to the power of n. So this one becomes 5 to the power of 2n is equal to 1 over 5 to the 4. If I'm re-expressing this, it's the same as 5 to the negative 4. So here I have the same bases, 5, 5. So 2n is equal to minus 4, which means n is negative 2. Now if I go back and put n in there, it'll make sense. N to the negative 2. Oh, also 625. I could have made that a lot easier. The square root of 625 is 25. But that was a good way of analyzing it too. So the square root of 144 is 12 squared, which is the same as 12 to the negative 2. So obviously negative 2 is n. And the last two we might as well do as long as we're here. Determine this. Okay, if this is true, determine this. So we're trying to figure out y, where y is bigger than 0. Okay, so that's interesting. So that's a power of 5, and that's a power of 2. So can't really do much with it. I mean, you could come close to figuring out what 10 power is to this. There's a way of taking logs of doing this. Interesting that this is in here. There might be an easier way of doing it. Well, 10 to the 1 is 10, and 10 to the 2 is 100. So it's going to be like 1.1 or 1.2. And that's one way of thinking about it. You could do that. I mean, you could try to find what power of 10 is close to 25. So to do that, you'd say, okay, I'm going to take 10, and I'm going to put it to exponent of 1.1. I get 12. And I'm going to take 10, and I'm going to put it to the exponent of 1.2. And I get 15, so it's around 1.4. I'm going to put 10, and I'm going to put it to the exponent of 1.4. And I'm going to try again because I didn't do it probably. 10 to the exponent of 1.4 is equal. There, very close, 1.4. So let's go a little bit lower. 10 to the power of 1.39. So right in between. So 10 to the power of 1.395. Higher, so 1.97. So 10 to the power of 1.39. Oh, 1.399, I think. 10 to the power of 1.399. Yeah, let's do that. So 10 to the power of 1.399, essentially 1.4, let's just say 1.4 to keep our life easier, is equal to 25. So that means it's equal, if 10 to the 2y is equal to 25, which is this, that means 2y is equal to that. So 2y is equal to 1.4, which means y is equal to 0.7, which means 10 to the negative 0.7. And you might say, oh, I don't understand how you're doing decimals. There's several ways to do decimals. You can do 10 over 7 is the same as, or sorry, 7 over 10, negative 7 over 10 is the same as 0.7. And that simply means that I'm going to take the negative, means I'm going to put 1 over 10 to the 7/10, which also means I'm going to take 1, 10 to the power of 7, and I'm going to 10 root it. That's what 1 over 10 to the 7 is. However, my calculator can indeed handle 10 to the power of negative 0.7. It should get a really tiny fraction. .19999. So it's essentially 1/5. Now there's probably a trickier way of figuring that out without cheating the way I did. But I don't know if I want to spend the time on it. I mean, 5 squared is a way of expressing that, and 2, no, 2 can't be expressed with that. And there's ways of figuring it out, I think. Probably connected to 100. So 25 times 4 is 10 to the power of squared, right? So that would mean maybe a quarter of that. I don't know, some connection that I can figure out. I don't know if my way was the right way. These you just resolve, and what they're getting you used to is that you can distribute exponents. So are they the same base? Yes, I got x and I got r. So I can just distribute their exponents. Let's distribute these ones first. I get 21 minus r. And what's the rule of exponents? When they're multiplying, you add them. So I get 21 minus r plus r. So I get x to the 21. Oh, I didn't distribute properly. That's minus 3r. 21 minus 3r. And then plus r. So I get x to the 21 minus 2r. And that's as far as you can get it without knowing r. So what do they do here? Well, just be careful you follow the rules. Same base? Yeah. So these are being divided. So what's the rule? You can subtract their exponents. So I just put 2m plus 3m as the top one. And I'm subtracting 1m. And careful, you've got to subtract the whole bracket. So 1m minus n. This minus distributes through. So I get minus m plus n. So I get 1m plus n makes plus 4n, n. So it comes out to 4 to the power of n, m plus 4n. Just make sure when you subtract the whole thing as a bracket. So distribution works even for exponents. What about something weird like this? What are they trying to get to here? Well, just keep this the same, right? And realize that this is 10 to the 10 minus p times 1 to the p. 1 to any exponent is just 1 over a to the p. So we get a 10 to the minus p divided by a to the p. So the rule is I take the top exponent, 10 minus p, they're the same base, and I subtract 1p. So I end up with 10 minus 2p. So the answer is a to the 10 minus 2p as an exponent. And that's all I can get. Let's look at this last one. So yeah, you have to apply the exponent to the 3 and to the x before you do anything. So you get 3 to the 6 minus m and x to the 4 times 6 minus m, which becomes 24 minus 4m. So that's one way of doing it. I've now resolved this entire thing. And it's essentially being multiplied by 1 to the m, which is just m, 1 rather, and x to the m. So it's essentially this whole thing over x to the m. Well, this is the only one with the same base, so these are the only ones I can subtract. So it becomes 3 to the 6 minus m times x, and minus 4m minus m becomes x to the 24 minus 5m. And that's all I can do. Notice I had to get the 3 separate to do this subtraction properly. There you go. That was painful.